and thanks for coming, everyone. Today we have IITH and Anson presenting their paper at IIIT 2023 on Learnable Spectral Wavelets on Dynamic Graphs to Capture Global Interaction. It's a super interesting paper, and I personally have a bias for spectral-based methods. So definitely very excited to hear about the talk. Yeah, so I think I will start by doing the speaker bios. So for today we have Anson Bastos, who is a PhD student at the Indian Institute of Technology, Hyderabad, IITH, India, under the supervision of Dr. Manoj Singh and Dr. Toyotaro Suzamura. And his research interests and work are in the areas of geometric machine learning, graph signal processing, topology, knowledge graph, and more. And we also have Abhishek Najeri. So sorry for the pronunciation of the name. Hope that's okay. Who is currently pursuing his master's at RWTH Anson, Germany, and his research interests are graph ML, time series, and NLP. I think we can get started for now. So I'll hand it over to you.
Okay, maybe I'll share my screen.
Yes, and also one thing to ask quickly, would it be okay for you to share the slides afterwards?
Sure. Yeah.
For people to see. Okay. Thanks.
Okay. Okay, so I hope my slides are visible.
Yeah.
So thanks for having us here, and I'll be presenting our work on learnable spectral wavelets and dynamic graphs to capture global interactions. So as all in this reading group would know, dynamic graphs represent structures where the graph structure as well as the node signals change with time or evolve with time. And the aim is to learn these representations, which can be used downstream for link prediction or edge classification or node classification. So much progress has been made in the domain of graph representation learning for static graphs. However, these methods do not work well in the setting of dynamic graphs. And so many researchers have tried many things, primarily applying a GNN in front of an RNN, or sort of GNN RNN models, or using autoencoders to learn the evolving features, or learning the parameters of GNNs that evolve with time. However, much of this work has been done, in the spatial domain, and sort of these give much priority to the local neighborhood and only captures the low-pass signals. In doing so, they avoid or they ignore the global interactions that may emerge, that may occur in the dynamic graphs. So just to motivate what is these global properties and why they're important. So consider this setting where it's sort of a bipartite SPM graph, where we have on the first row sort of a citation network of papers, and on the bottom row we have this group of readers. So now the task is to select users for a reading group, such that the interests are diversified, and you get to transfer and share and learn much knowledge, diverse knowledge. So the existing methods on dynamic graphs would being low pass, or sort of having this local neighborhood aggregation tendency, would just try to group users having similar interests together. Whereas what we would like to do is we would like to sort of have users which are far away interact with each other. So this is what we are talking about, or what we mean when we say global properties or global interactions. We want nodes that may not necessarily be nearby, but have certain meaningful properties to interact. The nodes which are farther away should interact with each other. And that's what we, so this is just one example where this sort of heterophilic, if you're aware of that term, property helps, right? So the hypothesis we have is that in this paper is that capturing global dependencies beyond this local neighborhood aggregation will enhance the representation learning for dynamic graphs. And this work is yet to be, before this paper has not been explored. So specifically, we look at this problem through the lens of spectral graph theory to learn these graph wavelets to capture these global interactions. So on why spectral graph wavelets, so some motivation here. So there are multiple reasons, some of them being the computational efficiency. You can compute these wavelets in linear order of time, which is linear in the number of nodes as well as the number of edges in the graph. Wavelets are generally sparser as compared to the full graph Fourier transform, and it gives a sense of localization in the vertex domain, and in that sense it has some interpretability property. And yeah, obviously while doing all of this, it does what we intend to do, which is capturing global properties in the graph. So the main research objective of the research question we ask here is that does incorporating global features using these spectral graph wavelets help in effectively learning representations of a dynamically evolving graph? So yeah, I mean, if there's any question, please feel free to interrupt in between. So is there any question till now? Or? Okay. So then I continue. So just to give a basic intro or a background as to what wavelets are in the classical signal processing domain. So we can think of a Fourier transform as sort of a signal transform which is obtained by sort of multiplying a basis vector, okay, for a given frequency, which is omega in this case, with the input signal f, and that will give you a sense or a knowledge of presence of the frequency in the entire domain, right? But it does not tell you about the location. So wavelets are a sort of a modification of the Fourier transform to sort of tell you about where in the time the signal occurs, right? And then by stretching, for example, in this case, you have a certain frequency, right? And then when you stretch the signal, the template, you get a lower frequency. And when you compress it, you get to know about the presence of a higher frequency. So as such, you can think of two axes. I'll be showing an animation later on, but basically, you can think of wavelets. You can think of it as a matrix structure. One axis has the scales, which will tell you of the frequencies, and the other axis will have the time information, which will tell you the location or the presence of the signal. So in this animation here, the sigma axis gives you the frequency or the scale information, and the delta axis tells you about the time information, where the signal or where the frequency occurs. So for a given scale or frequency sigma, what we do is we slide the template across, you know, the time domain or the time axis, and we get the knowledge of the presence of these frequency components. So one point to note is that this so these wavelets give a sense of localization in the time domain, not the frequency domain. But for graphs, as we'll see later, the vertex domain, which is the equivalent of time, is not continuous. It's discrete, right? So you can't talk of scaling and all that in that discrete domain. So we do learn wavelets in the spectral domain for the continuity, but essentially they're equivalent. So we'll come to that probably later. But yeah, so this is what classical wavelets are. And now connecting to the graph Fourier transform, so let's consider a ring graph, right? Which is sort of a time series maybe with signals f1, f2, f3, and this is the adjacency matrix representation for the graph. So I'm just motivating or connecting this classical wavelet transform to the spectral wavelets. So yeah, so if you consider the node f2, and we consider the gradient of the signal just before f2 and after f2, there is a signal incoming inside f2 and outgoing from f2, then we have sort of something like this: f2 minus f1, which is a gradient here, and f3 minus f2, which is a gradient after f2. And if we want to know the accumulation of the signal at F2, we just repeat this process again. We sort of take the inner product of the gradient with the with the gradient at F1, and then we sort of get the divergence at this point, which is nothing but the Laplacian matrix, right? And here in this case, it turns out, so D is the diagonal degree matrix, as we all may be aware, and E is the adjacency matrix. And in the ring graph, it turns out to be a circulant matrix. And the Laplacian of the circular, the eigenvalues and eigenvectors of the circulant matrix turn out to be the frequencies and the basis of the Fourier transform. And this is where the connection comes with the graph Fourier transform for general graphs. So as many of you would be aware of this. So so one point to note is that this Laplacian is a positive semi-definite, and so we will have this sort of eigen decomposition existing. And yes, so now the graph Fourier transform is simply the inner product of the corresponding eigenvector with the signal on the graph. So like in the classical frequency, in the classical signal processing domain, we had sort of inner product with the basis vector, the basis frequency with the signal. So here we have the same thing, right? Inner product of this basis eigenvector with the signal. And the inverse is similarly obtained by sort of multiplying this f cap with the eigenvector. Okay. So any questions still here? Okay, so I'm just covering a few basics before we start with the method. So now spectral graph wavelets, like I said, in the classical domain, we had the wavelets in the time domain. So here we'll have sort of these wavelets in the frequency domain, right? So lambda represents the frequency, and g of lambda is some function in this domain. And we define an operator Tg in the vertex domain that acts on this function f, which is the signals on the graph, by changing each component. Yeah, is there a question?
Just a quick question. Can you maybe repeat how this is relating to the eigenvectors as well? I think you had it in the equation, but just want to recap a little bit.
So which one are you referring to, the spectral graph wavelet or the graph for it?
Yeah, the spectral graph wavelet. Yeah.
Okay, yeah, we are coming to that. We are coming to that.
Okay.
Right. It's in the next slides.
Okay.
So yeah. So the so basically when we say that we'll find the graph Fourier transform, what we are doing is we have this, we take this inner product of the signal with the basis vector, the eigenvector, right? And we get something like this f cap, right? The transformed signal, which will sort of tell you about the magnitude of the signal, in that frequency component, right? In this case, L. So this function will sort of modulate that, right? It will, so let's say for the frequency L or lambda L, let's say it's in the low region. So g of lambda L is a bit low here. So we'll multiply that. So let's say your graph may actually be having a low frequency component. So f cap of L, this one, will be high, right, for the low frequency. But the wavelet, the wavelet function, as I call it, will sort of change it to have a lower value, right, for some reason, right, for some signal processing reason. I want to filter out the low frequency components, and so that's a simple connection, right? F cap is obtained by inner product with the eigenvectors and the basis vector, and then I further modulate it or change it by this particular filter function or wavelet function, and that's the connection in the spectral domain. Right? TG cap is in the spectral domain, right? So I think that answers your question, Andy.
Yeah,
okay.
Thanks. Yeah.
Yeah, so that's a simple connection. Yeah, it's once you come in the spectral domain, you just apply some filter function or a wavelet function, and yeah, you sort of get this operator. So it's as simple as that. So yeah, so now so this is still in the spectral domain, and we would like to know what this looks like so the wavelets would be in the time domain or on the vertex domain here, as we had wavelets on the time axis in the classical case. Yeah, so let's see. So obviously, if I have something in the spectral domain, I would like to take the inverse and then convert it to the vertex domain. So that's exactly what I'll do. I have f cap modulated by g and multiplied with the eigenvector as the normal inverse goes, right? You're just you're multiplying with the wavelet function, and so this will give you the operator tg, right? So now we would like to know what the wavelets look like. Okay, so this is just something I've mentioned with this operator tg, but how do I define a wavelet, right, on a graph? So then I'll consider the impulse function on the graph, where for a node n, I will have a 1, the red line represents a 1. So I'll have a 1 at this node and zeros elsewhere. And yeah, and so what will this be? So instead of f cap, I'll have delta cap. And we can work it out. Basically, this delta cap will be nothing but the conjugate of the eigenvector, right? Because
So the impulse function is just an indicator vector then.
correct. Yes.
Okay.
So it's like, yeah, I have a sort of an impulse signal, and then now what will my output look like, right? So whatever it will be, I'll get the wavelet vector at that node, right? Like I had in the
Right.
classical, in the classical case,
Right.
I had at a given location at a given time, I had something. So here I'll have that same thing for the given node, right? So
Yeah.
I'll have each one vector for each node.
Right. Yeah. Thanks.
Yeah, so the wavelet at node n would then look like something like this. Yeah, basically g of lambda. I'll just ignore the t for now. So g of lambda L into the eigenvectors conjugate into the eigenvector. So yeah, so that's a wavelet at node n, and I just multiplied with scaling factor t. So the scaling factor is nothing but the same stretching or compressing thing that we were talking about too. So it'll sort of help me learn different frequencies. We'll come back to that in some later time. Okay. Yeah. So this is just a little matrix visualization, matrix vector multiplication visualization. Also, now I just said that each node will have a vector. So then I'll have sort of a matrix where each column represents a wavelet vector for that node. And so this matrix is what I'll call my wavelet, right, of the graph at scale t. And it's very simple to obtain. You just take the eigenvector, multiply it element wise with the wavelet function, and then do a matrix vector multiplication again with the eigenvector. So you can just think of it as sort of a weighted average, a weighted sum of the basis frequency vectors that will inform how to aggregate the signals from the global graph. Right, so it just gives you a sense of like what kind of aggregation I want. Do I want to get global signals or local signals, or all sorts of things that were not possible with the local methods are now possible with wavelets. Right, so this was about graph wavelets, right? And now what we are interested in is learning wavelet coefficients. Again at scale t and node n, and this is nothing but the inner product of basically this wavelet vector at node n and the signal, right? So now this is a vector. So you take the inner product of a matrix with a vector, you get a vector, right? So this wavelet coefficients are what we'll use downstream for our learning tasks. But yeah, so any questions till here?
So the intuition for can you go back one slide?
Yeah, sure.
So just to clarify, so you said that the wavelets are a weighted sum of the basis frequency vectors. Like, can you clarify what you mean by signals from the global graph? Like, more precisely, like, does it encode the role of the node in the global graph, or how it interact with the frequency vectors and so on? Is a bit more clear on that.
Okay. So signals on the graph would be so that you can think of it as a vector, right? Sort of a one-dimensional feature for each node, and now I have n such features, one-channel features, right? So I have this sort of a vector for the graph, which now represents, which I'm calling signal, right? Each so that's the vector, I'm calling it as a signal, right? And the value at each entry will be like the value at that signal. So sort of this blue red lines at each node, you can consider this as a signal. So,
Okay.
and now what I'm saying that, so for a given node n, okay, how would I want to, so, okay, the local message, the basic message passing, the non-spectral, the spatial message passing methods would do is they would aggregate the local neighbors, right? The local one hop neighbors, and
Yeah.
and sort of collect information in that way. So that's one way to do this. But I could also say that, okay, now you give me the signals from 2 hops away or 3 hops away, or maybe
Right.
maybe from very far away, and I want to now aggregate or collect those signals, right? So it's the basic aggregation step. So now what these wavelet vector, what these wavelet vectors would help me do is it would so again, the wavelet vector is nothing, it's just a vector, right? At that node you have a vector, and
Right.
now to aggregate the signals, I would take the inner product of this vector with the signal, right, with f, right?
Okay.
And so and so that inner product will inform me of the aggregation. So if I do not want to take local neighbors, I will have a 0
Okay.
at that position, and if I have
So
to
it's
aggregate,
essentially a weight. It's a
yes,
weight vector you multiply with the signal. Okay, got it.
correct. And that will be informed by the the filter function will inform me of how to aggregate that. So if I want low pass, I will just have a ones for the one hop neighbors, and if I maybe want some high frequency signals, I'll have zeros at the connected nodes and ones elsewhere, something like that.
I see. Okay. Yeah. Thanks for the clarification.
Yeah, thank you for the question. So any more questions? Okay, so maybe we'll. So this was about the basics. So again, we intend to learn this or obtain this wavelet coefficients. So yeah, we obviously we can't do the entire eigen decomposition, so we approximate using in this implementation the Chebyshev polynomials, because it has been shown to work well in the static graph case. And it has been shown that it can asymptotically approximate any function in the domain of -1 to 1. So we sort of bring the frequency which is in lambda, which would be anything between 0 to lambda max, to -1 to 1. So that scaling has been done, and then we sort of have this function, this approximation, where the function g of lambda, g of y, is an infinite summation of ck times tk, where ck are some coefficients and tk is the Chebyshev polynomials represented by this recurrence relation. We in practice, we obviously truncate it to some finite value. It will not be going to the infinity, and whatever that finite order is, we'll call it the filter order, right? So that is for the approximation, and now we would like to learn this approximation, right? So basically we would like to learn the filter coefficients ck, because the tk is basically the the variables which we obtain from the Laplacian and so on. So ck is something which we would like to learn. Okay, so this is how we would go about doing it, right? So if you can, for now, just consider the static graph setting. We'll look at the dynamic graphs later. So we have this graph, right? And now I want to learn some vector, which is the filter coefficient ck. I would like to learn a vector for this graph. And so what I do is I initialize every node with some sort of vector again. You can think of it as a prior to the filter function. So if, for example, I would like to learn an all pass, or if I would like to have a prior of all pass filter, maybe I would have a ones in all locations. So I'll initialize all the nodes with the ones or something like that. And then I would like to perform some sort of message passing. This A here represents aggregate and U represents update. You can think of it as a normal message passing functions. And now, so after doing this, I would like to have a single vector representation for this entire graph. And so I would have a readout function which I represent by this pool thing here. And so this gives me a latent vector in dimension dp. I would then pass it to a two-layer MLP, which is a universal approximator, to learn the filter coefficient of this wavelet function, which we saw before. We can show that if we have an expressive enough GNN, and if we and since the MLP is a universal approximator, we ideally should be able to approximate any filter function or any wavelet function that we desire. So this was for the static case. Now we would like to learn this function, or this sort of wavelet function for the evolving graphs, right? So now what we would like to do is have these parameters also evolving with the graph. And so for that, we stick to the RNN, where the inputs would be the sort of signals on the graph, or the output learned from the graph signals. And this WT represents the GNN's weight parameters in the previous time step earlier, and the output would be the parameters which we would use downstream, right? So in the first step, we initialize with some. This is in the initial step, in the zeroth step. H0T would be the signals on the graph, and WT L-1 or WT0 would be some random or initial weight parameters. The RNN would then throw out an initial weight vector, which would be used in this GNN to learn the filter coefficients, and the output would then be fed back as it is in the RNN, and the process would repeat, right? And this is how we would go about learning the GNN parameters for the evolving graph. Yeah, so this is what I represent in the algorithm. Basically, you have some dynamic parameters given by the RNN that is given to the GNN to learn some vector, and which is further given to an MLP to learn the filter coefficients. And these outputs are then again given back to the RNN, and the process repeats for the dynamic case, right? So essentially, this is the main module which evolves the filter parameters for the spectral module, right? And how do we use it? We use these filter coefficients into the sort of wavelet approximators, which will perform this scaling operations, and then aggregate the signals and give it to the further downstream modules for the further tasks. So I just wanted to make a quick point on this. Okay, so any questions still here? Okay. So hope this is clear. But yeah, so this module is the main spectral module that we with which we intend to learn the wavelet coefficients. So yeah, on the scaling, so now once we have the filter coefficients, we would maybe, let's say, there would be a vector, and we would learn a single filter function, right? So now we in this case, this is a band reject function. Okay, so now we wish to sort of perform some kind of some kind of scaling or compression or whatever, and then do some, like, maybe learn a low pass or rather obtain a low pass or a all pass kind of a filter. So let's say I stretch it by 2 or have a scale of 1 by 2. So then the signal, or the filter response that was at 0.5 now comes to 1. So I'm sort of stretching this red function by factor of 2, and I'm sort of getting this kind of this blue thing. So now we can see that from the band reject, we reach a low pass, right? And then if I continue this way, I'll just keep stretching this till I get something like an all pass. I just allow all the frequencies. And so this scaling function is something similar to as we had in the classical domain, just that it was in the vertex and the time domain. And here we are doing it in the frequency domain. There is an equivalence between doing it in the frequency domain, and so we'll come to a case study. I'll not go into the theory right now, but we'll come to a case study where we'll see that how this stretching operation or scaling operation causes the wavelets to be diffused throughout the entire graph, and enables us to learn some global properties. So we'll come to that later on, maybe. Okay, so there's one small issue here with the spectral module. So previous works have found that for the lower frequency regions, the spectral GNNs have a diminishing factor, and this means that as we increase the number of layers, the low frequency information would just vanish, and we would have sort of a high frequency sort of a response. And so this is what is called as the unsmooth spectrum. So this was proposed in some work in ICML of 22 by Yang, I guess. So what it basically says is that and we have some empirical evidence for this, which will come to in the experiment section. But basically, it says that the lower frequency components have a higher diminishing factor as compared to the higher frequency regions, and so this impacts the performance downstream. So to mitigate this, we simply induce a low pass response using a spatial GNN module. And the parameters of the spatial GNN are learned similar to the spectral GNN, just that there are no wavelets or anything else, just simple low pass aggregation. Okay, so then our method can be summarized with these three components. There's a spectral component, which you've already seen. There's a spatial component to mitigate the unsmooth spectrum. And then there's an integration module to combine these two results. So something like you evolve the parameters. Again, this is the same thing that we had seen before. You give it to the spectral and the spatial module, which will learn the representations, and then they'll be combined in the downstream module. So here the HRM just represents a homogeneous representation module. Again, I'll not go into much details about this, but it just does is it combines these two into a sort of a homogeneous or same representations, and then gives it to one more layer of further aggregation, which could be a transformer or an MLP or a GAT layer or something like that to perform the downstream task.
So yeah, so just to clarify, the spectral module is a spectral GNN, which you use to learn high frequency signals. And the spatial module are standard message passing GNNs like GCN and GIN, which is for local aggregation only. Like it will not have too many layers. So it will be like limited by one WL test.
Okay. Correct, yes.
Thank you.
So this spatial module was required because without this, like I said, the unsmooth spectrum caused the low frequency response or signals to just vanish, and that was on the data sets that we tried on. We found that the low frequency was important, and so adding this helped in that case. So we'll come to the experimental section on that.
Okay.
So okay.
Before you go on, can you shortly explain how you combine the two outputs of the two modules? I know you don't want to go in detail, but maybe shortly.
Okay. Yeah. So I'm just thinking, how do I explain it in a way that it doesn't get too complex? So basically, what we do is we use something called as the random Fourier features, I guess. Right. So so it's sort of we just you can think of it as this combining it in a way like you maybe if I were to simplify it, oversimplify it, I would just sort of concatenate it. Maybe learn, or sorry, not concatenate it. I would sort of do some transformations, give it to an MLP, then apply some cosine and sine non-linearities on that, then concatenate it, and then sort of take a dot product, right? And what that would do is it would help me learn this sort of something called as a shift invariant property, such that because now since I've taken the sine cosine and then taking a dot product is equivalent to sort of preserving this distance property. Like if I have like A and B, and if I want to sort of have a sense of a distance between them, then dot product A, that the f of A dot f of B would be represented in terms of this cos or cosine of A minus B, and so I would have this dot product representing this or preserving this distance between them. So we just wanted that distance preserving property for some reason in the paper, and so yeah, so this is inspired by that random Fourier features property, and yeah, once we have done those things, then we further feed it to the aggregator module, which is like a transformer. So for the transformer, you could think that this HRM sort of learns some position encodings, or yeah, something like a PE for the dynamic graph. But yeah, does it help? I mean,
yeah,
it was a bit.
No,
okay.
It helps. Thank you.
Okay. Yeah. Thank you. Okay. So any further questions? Okay. So moving to the evaluation section. So we evaluate on 8 standard data sets where we have covered almost many of the tasks such as edge classification, link prediction, and node classification. The data sets represent the Bitcoin transactions. Elliptic also is one of the Bitcoin transaction data set. Some social network data sets such as Reddit and UCI, some synthetic data sets, and some bioinformatics data sets. The nodes range from a few thousands to a few hundreds of thousands, and the edges go from a few tens of thousands to a million nodes, million edges. And yeah, there are about hundreds of timestamps in this data set. So tens. So in some cases there are very few timestamps, and in some cases there are something about 100. So I would say these are medium-sized data sets. And so coming to the main link prediction results, so we see that our method significantly outperforms the baselines, and specifically the comparable baselines, which was evolve GCN, where they evolve the parameters in this of the spatial GNNs. So we see that our method, which evolves the spectral the spectral properties or spectral information of the graph, has a huge jump, right, compared to these the only spatial evolving modules. And this shows that it's important that along with learning the parameters for the evolving graph, you also learn the evolving spectra of the graph. And a similar observation has been found for the edge and node classification, where our method outperforms the baselines on these settings. So since there are many modules in our framework, so we try to sort of do this ablation where we first study the sort of these okay, we first study the GWNN, where there are, so these people also have used wavelets, however they are non-learnable sort of. It's, I think, using heat kernels or something. And so we see that our method significant. Oh, now okay, this was for the static setting, but we tried using things from static setting and seeing why they don't work, right? As we said in the beginning. So we see that the non-learnable wavelets do not perform so well, right? And so it is obvious that we need to evolve this learnable. Sorry, we need to evolve these wavelets for the dynamic graph case, right? Similarly, since we observed that the transformers out of all the aggregators perform the best in our case, so we also did a ablation sort of on the static transformers, and we find that while they do have promising results in some datasets, and this on the synthetic dataset, in real world the performance does suffer, compared to evolving the spectra of the graph. And then obviously without the spectral module, we perform an ablation and we find that the results suffer further. We further do one more experiment where we have the spectral module. It is learnable, but now it doesn't evolve with time, right? There's no RNN and all. There's just the spectral module which learns some spectral weights and spectral coefficients, but that's sort of static in time and doesn't evolve, right? It's learnable, but it doesn't evolve. And we note that yeah, the results are obviously less than our best configuration, but then it's also lesser sort of than without using any spectral. So essentially what I'm saying is that if there is no spectral module, well, you have 0.046, and then as soon as you have this static spectral module which learns the spectral, which learns the filter functions and all, but then it doesn't evolve, so then the results suffer, right? So for dynamic graphs, you can't assume one size fits all kind of a thing. You have to evolve the spectral properties with time. So this was an important finding. And then obviously without this is the unsmooth spectrum phenomenon, where without the spatial module, our results also suffer further, and in fact it drastically suffers. So this is more or less, I feel, a property of these data sets, where they probably have much low pass signals or low frequency characteristics, and so they suffer without the spectral module. And obviously without the HRM or the homogeneous representation module, again we see a deterioration in the results. we further do some studies to find out the effect of the filter function parameters, such as the wavelet scale, the scale that we were talking about, and the filter order of the Chebyshev of polynomials. So we see that in general, higher scales seem to, benefit the task, and the reasoning we have is that at the maximum scale, the filters will learn to sort of select the useful components of the signals and sort of ignore the not so useful signals. And as you perform sort of scale or modify this filter function, you sort of induce some kind of a noise, or you sort of bring in some signals which is not so useful, which it kind of brings in further noise, which may be difficult, because these wavelet scales are not learnable, right? They are sort of parameters. These wavelet scales are hyperparameters, and the model may find it difficult to learn what is useful and what is not if you just scale it. But anyways, we find that in some cases it does help, right? Versus and for the filter order, it seems to be dataset dependent. So for the smaller datasets such as brain, we observe that having a lower filter order helps, whereas on the larger elliptic dataset, the medium filter order helps. So it also has to do with the structure. So for example, brain, in case of the brain dataset, we would like to have some sort of local neighborhood aggregation which respects the structure, and so we see some low frequency characteristics, whereas in the elliptic dataset, so elliptic is a dataset where we have to identify these illicit transactions, and so illicit transactions would generally be like a fraud user trying to interact with a genuine user, and so on. So you sort of have these heterophilic signals, and you want to probably have some kind of a non-low pass aggregation. So here we see that we need little more complex filters, and so probably. But yeah, the sense is that we need to sort of tune these parameters, and it's dataset dependent. And finally, we do a case study where obviously on the brain dataset, we try to see what kind of wavelets are learned for this yellow node which I'm circling. Yeah. So this node is at the end of the tip of the brainstem region, and we see that for the scale 1. A band reject filter is learned, and yeah, it sort of tries to concentrate the green nodes, sort of show that okay, high attention is paid to those nodes, and all of it is somewhere around the brainstem region. So we sort of have this structure preserving representation. And then when I further perform some scaling, I 10 times stretch it, and then we see that the wavelets are a bit diffused. So they spread further, but most of it is again concentrated in the brainstem region, with a few of the green nodes appearing a little away. But yeah, again, the structure is respected again. And then when I further stretch it in order to get an all-pass kind of a filter response, now what we see is that it's much more diffused. We see shades of green and light pink throughout, indicating that now the aggregation does consider much larger region, but we still see that the structure of the brainstem is still respected. So this is where we said that the wavelets respect the structure of the graph. So for example, this is not a trivial property, right? If I were to take a transformer and do some aggregation, it would just take over fence sort of an n square aggregation, and that would miss the structure, right? It would not consider the structure. It would just take similar features and then sort of group them together. But then wavelets are more sparser and more in that sense, because you see, okay, even though it's considering much of the graph, but it's learning to focus only on the structurally similar components, and yeah, and then probably aggregate the other useful components while being a little sparser. So this respects the structure of the graph while also being computationally efficient, and so yeah, and that's where it benefits in the sense of computing these global properties while being computationally efficient. Okay, so before we go further, any questions, Delia?
Have you run this same thing on the SBM synthetic model? Does it also highlight communities and so on, or do you expect it to?
Okay. So no, we haven't run it. It would be an interesting thing to do it for these SPMs and for the datasets. But yeah, I would like, for example, on the elliptic dataset where I said that there would be some heterophilic signals, I would expect it to sort of actually have this signals which are not so local to each other, which are sort of diffused or more, or have this high frequency characteristic. It would be an interesting thing to do for that. We haven't tried that, but so the thing why we tried it on the brain dataset was because here we actually had sort of some structure, right? And we wanted to show that our method learns to respect that structure. It would be a little more complex on the SPMs, probably. So depending on the task, right? So if SPMs, if the task were to find out, okay, so in the first time step, I want to say that nodes belonging to the same graphs or same groups should be represented in the same class, and then I want to invert that, right?
Yeah.
So then I would sort of have some kind of a toggling frequency characteristic. I would have a low pass and then a high pass. I doubt things. I mean, I would not say our method is perfect, and I doubt that such transitions would happen. Yeah, but
I think it'll be interesting to see what happens.
Yeah, it'll be definitely be interesting too. Yeah.
And I think this has a lot of potential in like interpretability for temporal graph, which is not really touched upon that much in the literature. So if your spectral wavelet can give you some idea about which area in the temporal graph are that you should focus on or undergoes changes and these kind of things, I think that could be super interesting. So like you can compare the wavelet visualization from different points in time. And let's say you have some sort of change point or anomaly that happens in between. So you go like you change your distribution. So let's say the graph goes from like SBM model to BA model, or like a difference inside a graph model, and you can see that the wavelet behavior are actually different, and you can pinpoint which nodes have the most different behavior, or these kind of things. So that could be interesting. But it's just like some thought that like when I see this visualization.
Yes. I mean, yeah, definitely there's much more future works to see in terms of, like you were saying, change point detection and stuff. So for example, on this brain data set itself, if we, sort of have this kind of a visualization and we are able to say that, okay, now things are local, and then, all of a sudden we have some kind of a global phenomenon happening, and we're able to capture that, and probably it would definitely give some confidence in terms of decision making. In terms of interpretability. So I think definitely there's much more work to be. It's not like we can just take this model and probably apply it, but there's some work to be done in that direction. So coming to the limitations on that lines. So the current implementation uses sort of polynomials to approximate the filters, and we know that these have certain issues in generating certain filter functions. Also, there's one more issue in the current framework, which is captured in, again, I'm not going into the theoretical details here, but in one of the lemmas of the paper, we show that there are some errors which could accumulate over time steps, and then this could cause some stability issues. So, and this is because of the framework that we have used, right? We have used the RNN to sort of depend on the previous filter, and then learn the filter of the current time steps and the future time steps. So this could cause some stability issues as well, we've seen. So we don't know the answer to this, but the better certain better optimization techniques could be devised to obtain the desired filter response to sort of mitigate this. And similarly, for the unsmooth spectrum, as of now, we have induced sort of forcefully induced low frequency signals or low frequency characteristics separately. So probably we could learn better filters to avoid this additional module. And then again, since we need all these multiple components, so can we have a single component which performs both expressive filtering as well as this effective aggregation for the temporal graph, dynamic graph case? One interesting future work is that, okay, so as of now we are using these RNNs along the temporal axis, which is still in the vertex domain. So can we sort of get rid of it? Can we make our method fully spectral by performing this Fourier transform in the graphs as well as time domain jointly, right? Can we do that? So that would be another future direction to look into. So yeah, to summarize, we propose a novel approach for learning spectral wavelets on dynamic graphs in order to capture global dependencies, and we build a framework around it that integrates the spectral features into the spatial features for the evolving graphs. So effectively, from the promising results obtained, we can say that local as well as the global properties are learned effectively, and while respecting the graph structure and being sparse and computationally efficient. So the key takeaway of the talk would be that as a graph evolves with time, the spectra of the graph also evolves, and then learning this evolving spectra may enhance the real world applications on dynamic graphs. And we encourage the community to look into this aspect as well, along with RNNs, CNNs, and evolving this in the spatial domain. We should also look into the spectral domain. So yeah, that would conclude the talk. Any questions?
Yeah, thanks for the great talk. I do have more questions, but I will let the others ask the question first. Does anyone want to share a question first? Okay. So I guess I will get the discussion more started, though I have asked a ton of questions. And thanks for the super interesting talk. I think there's a lot of potential room here, and it's a very novel approach on temporal graph that goes beyond just taking GNN and RNN and smash them together. So, so one thing I want to ask is the time complexity. You briefly mentioned it at the beginning. So what are the time complexity that you consider here? When you talk about scalability, what's exactly the complexity in terms of number of nodes and edges?
Okay. Yeah. So so there are multiple modules here, and that kind of causes some scalability issues practically. But asymptotically speaking, the yellow box here, it's just a sort of message passing plus some MLPs. So this would be an O of E, maybe. The spectral itself is O of E due to the approximation. Spatial would be O of E. HRM would be again a constant time, that would not have any message passing, so constant, maybe O of N. Okay, O of N into. The only thing, so okay, in the aggregation module, since we use the transformers, so we use a sparse variant of it, but if you use a full variant, it would be like O of N square. So it depends. Yeah, it depends only on the message passing frameworks that we've used. But if we sort of have all of them into an O of E, we overall have an O of E complexity. So
right.
And yeah, if for bounded graphs, it would be O of N if the degree is bounded. So then you would have a linear complexity. But yeah, having said that, since there are multiple modules, we have observed that scaling this practically is a bit of a challenge due to the many components in there. But yeah, asymptotically, it would be an O of N plus C. Okay.
Sounds good. And also, based on my understanding, this only works on discrete time dynamic graph, right? So you need to have discretized snapshots. So have you think about how to extend this to continuous time dynamic graph, or how you would go about it?
Yeah. So you're right in your understanding that this is built for discrete time dynamic graphs. But yeah, if you have to extend it to the continuous case, probably I don't see much of a challenge in there, except let me see. So in the spectral module, probably yeah, right. So probably we would just have to feed in some, so as they normally do in the continuous time setting, right? They would have the time aspect, and they would encode that, right? Encode the temporal features into the module, right? So I would probably expect that yeah, having the temporal aspect fed into as some feature over here or somewhere, we can probably deal with the continuous time case as it's normally done. So here, obviously, in this current setting, we have just considered the discrete case. So there's no time going as an input, since we consider it sort of maybe uniformly sampled or something. But yeah, in the general case, we can just probably feed time as a feature again and into one of these modules, and that should, I mean, it may not be the best approaches, but that looks to me as one of the approaches to tackle the continuous time.
So you kind of need to slice the continuous time dynamic graph into snapshots and discretize it, and then give some information about how much time have passed between each slice, and then feed it to your model, right? So you still need to discretize the graph in some way, because otherwise the notion of the spectral wavelet wouldn't exist, because if it's just a bunch of edges and doesn't form a global graph.
I'm afraid I didn't understand it completely. So could you repeat that part, the last part where you said you slice
So you
it?
need to discretize the continuous time dynamic graph into a global graph, into a static graph, like into a graph snapshot, and then you can apply your method on top, right? Because
okay,
the wavelets are defined on the global level on the graph, because that's the difficulty with continuous time dynamic graph, is that it's hard to define the global graph at any given time.
Okay, so you're saying, okay. So, but then even in the continuous case, I would have snapshots, right? But okay, I see your point. So probably where I see this would be an issue is that, so for example, if you were taking a Fourier transform, right? Fourier transform along the temporal axis, there I would need the signals to be sampled at uniform time, right? Whereas in the continuous case, I would have some things, some non-uniform things, and there it would be an issue. And then we would have to probably sort of make it uniform by interpolating or something. In this particular case, yes, obviously, if I cannot do it on infinite graphs, obviously, but yeah, I would, for the continuous case also, I would take some snapshots at some time step, and then I would apply this method, right? The RNN or anything doesn't require, it just requires it to be a sequence. It doesn't require it to be uniformly sampled or something. So as long as we, at least that's my understanding and belief, that as long as we feed in the, obviously there will be snapshots, and as long as we feed in the temporal information, I think we should be good. For the,
okay.
In the sense.
Yeah, sounds good. Yeah, thanks for the great talk. So we're at the end of the hour, but if there's any questions, feel free to send a question to our speaker as well. And I will so great to have everyone here, and thanks for the presentation again. And I will see you guys next week at this time. Okay.
Thank you very much.
Thanks, everyone.
Thank you.
See you.
Thank you.